I want you to imagine, just for a moment, that you are walking into a heavy industrial foundry right in the middle of India.
Oh, yeah. You really have to put yourself on that floor mentally to grasp this.
Exactly. I mean, it is scorching hot. The air is thick with, particulates and dust. The noise is just this absolutely deafening, continuous roar.
Right, you're surrounded by heavy machinery, molten metal, sparks flying everywhere, soot.
Yeah, and to the untrained eye, it just looks like pure, unadulterated chaos. Like just brute force industrial production operating at the absolute limit of physical endurance.
Just total sensory overload.
But if you are trained to see the invisible structures beneath all that chaos, you aren't just looking at fire and metal. You're watching millions of dollars floating away completely invisibly into the hot air.
Literally just venting into the atmosphere.
Right. So welcome to the deep dive.
Mhm.
We're going completely under the hood of India's MSME energy infrastructure today.
The micro, small, and medium enterprises. It's a massive, massive sector.
It is. And our mission today is to look at how tiny, like almost imperceptible mechanical leaks are quietly destroying these massive profit margins. We're looking at why this whole run-to-failure maintenance model is deeply incentivized by the local economy.
Yeah, that part is wild.
And we'll get into how simply mapping out energy data is becoming a literal superpower for an entire subcontinent.
We've got some incredible source material for this too. We're pulling from an operational blueprint called Restorative Engineering, which focuses on energy savings performance contracts, or ESPCs.
Right. And we're also looking at strategic documentation from the Sanisha knowledge sharing platform.
Which is doing some groundbreaking work on tracking all this.
Okay, let's unpack this, because I want to start right back on the grimy floor of that heavy foundry cluster we just walked into. We have to look at the beating heart of these operations, which is, well, it's the cupola furnace.
Yeah, the cupola furnace, I mean, it dictates the rhythm of the entire foundry. If you want to understand the energy draw, you have to look directly at the forced draft blower attached to it.
Because melting iron isn't easy. It requires extreme sustained temperatures.
Right, which in turn requires a continuous, massive, high-pressure supply of combustion air.
And the forced draft blower is it's the mechanism driving that pneumatic volume.
Exactly. And it is an incredibly energy-intensive process. The operational data shows these MSME foundries are just bleeding capital through consistently punishing electrical overhead.
I mean, the power bills are astronomical.
Yeah.
So if I'm a foundry owner, right, and I'm looking at my overhead and my electricity bill just spiking every single month, I'm looking at this giant roaring furnace.
Yeah.
And this massive blower motor. And I'm assuming, well, it simply takes a ton of power to melt metal. High power bill equals a power-hungry machine.
Which makes logical sense on the surface.
It does. But the strategic documentation from that restorative engineering blueprint calls this an illusion of technical failure.
Right, an illusion.
Treating a high power bill by just, paying it, or complaining about the baseline grid electricity rates, the text says that's treating a symptom. But if the electricity bill is too high, isn't the obvious answer just that the machine uses a lot of power? Like, why does the source frame this as an illusion?
Well, to understand that, we have to apply what the text calls the first principles operator directive. Specifically, the very first directive, which is locate the friction.
Locate the friction, okay.
Yeah. The text argues that thermal and pneumatic energy, it dissipates primarily at the mechanical joints, long before it ever registers as an electrical fault.
Oh, interesting.
Right. So the directive urges operators to audit the physical structural connections before even touching the electrical or digital stack.
So you're saying what we're seeing in these MSME clusters is it's a textbook case of operational process failures perfectly mimicking technical bottlenecks.
Exactly. The electrical stack, the motor, it's working exactly as it should under the circumstances. The real bottleneck is an unaudited mechanical leak.
So the electrical spike is really just a downstream symptom of like a physical plumbing issue.
You hit the nail on the head. And the source data points to something frankly staggering here. Up to 20% of the combustion air generated by that forced draft blower.
Wait, 20%?
20%. It is leaking directly from the tuyers before it even reaches the combustion zone of the furnace hearth.
That is, I mean, losing a fifth of your combustion oxygen before it hits the fire is a massive structural failure.
It's huge.
For you listening, the tuyers are the physical injection ports, the nozzles connecting the air delivery network right to the furnace. And given the brutal operating environment, I mean, the constant thermal cycling, the extreme heat, The vibration.
Right, the mechanical seals around those ports are just degrading constantly.
But wait, how does venting 20% of your air translate into a massive, crippling electrical failure at the blower motor? I still don't quite get the connection there.
Ugh. Okay, so the downstream compensation is where the electrical penalty really compounds. We have to examine the fluid dynamics of the air network piping itself.
Okay.
The documentation notes that in these MSME foundries, the pneumatic piping is often improvised, it's poorly designed.
Right, it's not exactly aerospace engineering.
No, not at all. It features multiple sharp 90-degree bends rather than, swept curves.
Because 90-degree elbows are just cheaper and easier to weld together on the fly.
Exactly. But every single sharp bend introduces massive pneumatic friction and turbulence. Now remember, the forced draft blower is driven by a heavy-duty three-phase induction motor.
Right.
Because the air delivery network is venting 20% of its volume straight into the room at the tuyers, and because the remaining air is fighting through highly restrictive turbulent 90-degree bends.
The motor is basically pushing air through a leaky bent straw.
Yes, perfect analogy. And because of that, that induction motor is forced completely out of its optimal load curve. It has to draw maximum amperage continuously just to maintain the minimum static pressure required to keep the furnace at melting temperature.
Oh, wow. So the motor is operating in just a constant, unending state of overload.
Constant overload.
It's pulling excess current purely to compensate for the pneumatic friction and the sheer volume loss at the injection ports.
Right, and so the thermal limits of the motor's insulation are being constantly tested. I mean, it is running incredibly hot, fighting all that pneumatic resistance.
So eventually the insulation just breaks down.
Exactly. The windings short out and the motor fails. It dies.
And the foundry owner sees a burnt-out motor and a massive electricity bill. So they just log it as an electrical failure.
Yep. But the root cause is purely pneumatic and structural. The electricity bill isn't high because the motor design is flawed. The motor dies because the pipes leak and the routing is geometrically inefficient.
The visible symptom entirely obscures the actual bottleneck. The owner thinks they have a complex electrical grid issue, or maybe they just bought a bad batch of motors, when what they actually need is basic industrial plumbing and seal maintenance.
Basic nuts and bolts maintenance.
Which brings up the most glaring question. If the root cause is just a leaky seal and bad pipe geometry, why does the system remain broken?
Yeah, that's the big question.
Right. I mean, if you are bleeding capital, you patch the leak. The fact that they don't points to a deeply entrenched incentive structure keeping this specific ecosystem running to failure. And the source text dives into this specific microeconomy around these three-phase induction motors, and it is a completely misaligned ecosystem.
It really is. The blueprint uses this framework called the 6 lenses. Specifically, we want to look at lens 4, which is secrecy and legibility.
Okay, lens 4.
Right. Lens 4 asks us to identify the beneficiaries of obscurity. Basically, who extracts value when the operational truth remains hidden? Who wins when the foundry loses?
Wow. Beneficiaries of obscurity.
Yeah. And in these heavy foundry clusters, the primary beneficiaries of this obscurity are the local motor rewind shops. When that overstressed induction motor inevitably burns out, the foundry owner doesn't capitalize a brand new motor. They lean right into that run-to-failure culture. They pull the stator, send the dead motor out to a local rewind shop, and just have the copper coils replaced.
Now, rewinding is pretty standard practice in heavy industry, globally. But the text points out that these specific motors in these MSME clusters, they're being rewound 6, 7, maybe even 8 times over their lifespan.
Which is way too much.
Yeah. The issue isn't the rewind itself, right? It's the cumulative degradation of the motor's core efficiency with every single repair cycle.
Exactly. The electrical engineering reality of a local rewind shop is, well, it's brutal on the motor's baseline efficiency.
Walk us through that. What actually happens?
So when a stator is stripped, it's often baked out at incredibly high temperatures to remove all the old varnish and resins holding the old wire in place.
It literally set it on fire, basically.
Basically, yeah. And this extreme thermal cycling degrades the laminated steel core of the stator itself. It breaks down the interlaminar insulation.
Oh, man.
Right, which drastically increases eddy current losses and hysteresis losses in the magnetic core.
So you're permanently altering the magnetic properties of the steel.
Yes. The magnetic flux characteristics are permanently damaged. And furthermore, local rewind shops, they're doing this by hand. They often don't pack the new copper windings as tightly as the factory automated processes do.
So there's more air in there, which means higher resistance.
Exactly. So a motor that rolled off the assembly line with, say, an IE2 efficiency rating of maybe 85%,
Okay.
it might drop down to 80% after that first rewind, then 76% after the second, and it can easily approach the low 70s after a half dozen rewinds.
That is wild. So the motor requires more and more current to produce the exact same shaft horsepower. The foundry owner is trapped in an accelerating death spiral of efficiency. The pneumatic leaks strain the motor burns out. The rewind shop repairs it, but degrades its base efficiency. So then this degraded motor is put back onto the leaky pneumatic system,
Which means it has to work even harder.
drawing even more power, running even hotter, leading to an even faster burnout cycle.
It's a vicious cycle. And looking through Lens 4, the local rewind shop's entire business model relies on that run-to-failure culture.
Wow.
Yeah. If the foundry actually audited their pneumatic lines, if they sealed the tuyers and installed a highly efficient motor that operated well within its thermal limits...
The rewind shop loses a recurring revenue stream.
Exactly. The rewinder's margins rely on the continuous decay of the foundry's mechanical baseline. The foundry absorbs the entirety of the operational loss through inflated power bills and continuous rewind fees.
And the true bottleneck is just hidden behind this very comfortable, normalized narrative of, routine maintenance.
Right. The owner just views periodic motor bring-out as an inevitable cost of doing business in a really harsh thermal environment. They don't even question it.
So a local rewind shop acts as what the text calls the control point owner in this scenario. They own the critical motive power choke point.
That's exactly right.
Okay, so identifying that the system is rigged to extract capital from the foundry is the first step. But the restorative engineering blueprint lays out an actual surgical intervention to seize that control point away from the rewind shop.
And it's a brilliant intervention.
It is. Here's where it gets really interesting for you listening, because the mechanical intervention proposed is incredibly pragmatic.
Yeah.
You audit the air delivery network, you find the friction, you apply high-temperature refractory sealants to the tuyers, right?
Right.
Which the text notes yields an immediate 5% overall energy savings.
Just from plugging the holes.
Just plug in the holes, and then you restructure the pneumatic delivery.
Yeah, you cut out those highly restrictive 90-degree elbows we talked about, and you weld improper swept bends. That reduces the internal fluid turbulence.
And smoothing that airflow path removes enough pneumatic friction to yield an additional 3% in energy savings.
Right. So we are looking at an 8% baseline reduction in energy consumption strictly through localized mechanical plumbing optimization.
And that's before we even touch the motive power.
Exactly. Before the motor is even looked at.
But then, the final step of the mechanical intervention is scrapping that endlessly rewound induction motor entirely. You just throw it out, and you capitalize a brand new premium efficiency IE3 motor.
Yep.
So combining the sealed pneumatic network, the optimized pipe geometry, and this IE3 motor, it creates a massive immediate plunge in the foundry's monthly electrical draw.
It drops off a cliff.
But, and here is the friction. The financial friction here is obvious. These heavy MSME foundry clusters operate on razor-thin survival margins. I mean, they're barely scraping by. The capital expenditure, the CapEx required to buy high-end IE3 motors and rebuild industrial piping, that money simply isn't sitting in their operating accounts.
No, it's not. The lack of CapEx is the primary barrier to adoption across the entire sector. If they had the cash, they'd buy new motors.
Right.
But this is exactly where the Energy Savings Performance Contract, or the ESPC, becomes the vehicle for the intervention. The ESPC model relies on a zero CapEx upgrade for the foundry operator.
Zero out of pocket for the foundry.
Zero. The independent operator or the startup proposing the fix, they finance the physical upgrade entirely themselves.
Oh, wow.
Yeah. They buy the IE3 motor, they pay for the piping modifications, the high-temp sealants. They take on the complete financial risk of the hardware up front.
By absorbing the OPEX, the operating expense, the operator creates what the blueprint calls an asymmetric advantage.
Right. They are no longer just a vendor trying to sell a shiny new motor. They are a guarantor of operational reliability.
Okay, let me push back on the risk profile of this arrangement, though, because I'm trying to put myself in the shoes of the independent operator here. I just deployed thousands of dollars of my own capital into someone else's heavy industrial facility.
Yeah.
I've upgraded their pneumatics. I've installed a premium motor. But the legal infrastructure in these hyperlocal MSME clusters isn't exactly... well, it's not always robust enough to enforce a complex, multi-year performance contract.
Yeah.
What stops the foundry owner from just, locking the gates, keeping my hardware, and absorbing 100% of the energy savings themselves.
Yeah, the counterparty risk seems astronomically high, right?
It seems like a terrible idea.
It would be if you relied purely on a paper contract. The vulnerability is absolute if you just have a signed piece of paper.
Yeah.
And that is exactly why the framework relies on First Principles Directive #3, which is control the metric.
Control the metric.
Right. You do not touch a wrench. You do not capitalize a single piece of hardware until you have established the data baseline. The operator must install their own ruggedized energy monitoring hardware, like an edge compute sensor or an industrial IoT clamp meter, before the intervention even begins.
So you prove how bad it is first.
Exactly. You establish a mathematically undeniable baseline of the system's energy consumption while it is still operating in its degraded, leaky state.
But deploying IoT clamp meters in a heavy foundry environment, that isn't trivial. You are dealing with extreme ambient heat.
Very high heat.
Heavy particulate dust that fouls up delicate sensors. Massive electromagnetic interference from all the high-voltage equipment around it.
Yeah, it's a nightmare for electronics.
So the baseline data gathering itself requires industrial-grade, shielded edge devices.
The hardware must be completely hardened, but the data it produces, that is the true control point. You log the exact amperage draw of the failing system, you let it run for a bit, get the average. Then you execute the mechanical upgrades. You swap the motor, seal the pipes, and then you measure the power draw of the optimized system using that exact same sensor.
So the validation signal is the delta between the two.
Exactly. The entity that measures and verifies that exact power drop, they control the billing cycle. The ESPC is structured so that the operator extracts a specific percentage of that monthly delta. So if they save the foundry $1,000 a month in electricity, maybe they take $500.
So the foundry's operational overhead drops immediately from day one without a single dollar of CapEx spent on their end.
Yep. And the operator secures a high-margin recurring revenue stream.
That's brilliant. The text is unambiguous about the power dynamics here. It says, he who owns the baseline data dictates the contract terms.
It's the golden rule of this whole system.
You identify a high-impact control point using simple payback logic. The intervention costs X, it saves Y every single month. The operator captures a percentage of Y until the hardware is paid off, and then continues to extract yield on the optimization. But to enforce that logic, the data must be irrefutable. You align the financial incentives perfectly. The rewind shop we talked about, they were financially incentivized by failure.
Right. The more it broke, the more they made.
But the ESPC operator is financially incentivized by maximum efficiency and total system uptime.
You effectively dismantle that beneficiary of obscurity, and you replace them with a transparent, data-driven entity that is entirely aligned with operational optimization.
So everyone wins, except the guy doing the bad rewind.
Basically, yeah.
Well, if the simple payback logic is this irrefutable, and the ESPC model completely bypasses the CapEx bottleneck we talked about, human greed alone should have scaled this across the entire Indian subcontinent by now.
You would think so, yeah.
Right. Every independent operator with a line of credit should be swapping motors and sealing tuyeres in every single cluster. The fact that the source text is still analyzing massive energy bleeds in these foundries means the market hasn't solved this. So why is this intervention still isolated?
That is the million-dollar question. And the barrier to scale here isn't financial and it isn't mechanical. It is informational.
Informational.
Yeah. To understand this, we have to analyze the strategic documentation from the Samyuksha platform.
Right, the small and medium enterprises.
Yeah.
Energy efficiency knowledge sharing platform.
Exactly. Samyuksha is a massive initiative. It's backed by the Swiss Agency for Development and Cooperation, the Bureau of Energy Efficiency, TRI, and the MSME Ministry in India.
Serious heavy hitters.
Yeah, serious institutional backing. And they're aggregated data points directly to the core friction here. In the MSME sector, fragmented knowledge is a structural, systemic barrier to adoption.
Fragmented knowledge. So we are looking at industrial clusters in places like Rajkot, Howrah, Coimbatore, Pune. These are massive localized economies.
Right.
But they're operating in almost total informational isolation from one another.
The isolation is profound. I mean, let's look at the data from the Samyuksha 11th meeting presentation. They mapped out the total energy conservation potential across all these MSME sectors. And the breakdown is highly, highly revealing. They found that 54% of the energy saving potential requires replacement. meaning capitalizing new, efficient equipment.
Like the IE3 motors.
Right. Then 24% requires retrofits, which is integrating variable frequency drives or advanced controls into existing machinery.
Also requires some capital?
Yes. But a massive 22% of all potential energy savings falls under best operating practices.
Best operating practices or BOP?
Yes.
Now, 22% implies no CapEx,
Yeah.
no ESPC contracts, no new hardware.
Yeah.
That is energy being vented directly into the atmosphere simply because the floor operators do not know the optimal parameters for running their existing equipment.
It is entirely behavioral and informational.
That's tragic.
It is. BOP encompasses incredibly basic operational hygiene. It's the difference between leaving a heavy furnace idling at high fire during a multi-hour shift change versus just manually throttling it down. It involves calibrating the air-to-fuel ratio manually, or even just maintaining the V-belts on the blower drives. The text points out that a slipping V-belt can cause a 10% loss in power transmission efficiency before the forced draft blower even turns.
So if a belt is slipping, you just tighten the tensioner.
Right.
If a tuyere is hissing, you patch it with some clay.
Exactly.
But the operators are blind to the compounding energy cost of those minor mechanical failures. Nearly a quarter of the energy waste in these heavy industrial sectors is purely an awareness deficit.
And the tragedy of this fragmented knowledge is really visible when you compare specific clusters side by side. The Samiksha documents note that the Rajkot Foundry cluster, they focus heavily on formal energy audits.
Okay.
While the Howrah cluster has developed a specific focus on identifying and implementing those best operating practices.
So they had different specialties.
Right. The Howrah cluster might optimize their V-belt tensioning protocols and air pressure ratios, capturing a large chunk of that 22% savings.
Yeah.
But because these industrial nodes are geographically and sociologically siloed from each other, the optimized BOPs from Howrah do not naturally propagate over to Rajkot or Coimbatore.
Because they're competitors, right? Or just too far away.
Both. The friction of information transfer between competing low-margin industrial clusters is immense. They don't have time to hold conferences and share tips.
So an operational breakthrough in one cluster remains completely dark to the rest of the sector.
Exactly. And the Samiksha initiative is attempting to build that connective informational tissue between these fragmented nodes.
They're aggregating and distributing cluster manuals, right?
Yeah.
Detailed project reports, localized case studies. They are attacking the structural secrecy.
Yes. Returning to Lens 4, that secrecy and legibility framework, the secrecy here isn't malicious.
With the rewind shop.
Right. The rewind shop actively obscures the truth to protect a revenue stream. The MSME clusters, they obscure the truth from each other simply due to structural inertia, geographic distance, and the survival-driven myopia of low-margin manufacturing.
You just have your head down trying to survive the day.
Exactly. So Samiksha's mandate is to force that fragmented operational knowledge into a legible, accessible format for everyone.
Well, you cannot optimize a system across an entire subcontinent if you don't know where the inefficiencies are concentrated.
No, you can't.
So the Samiksha documentation details a specific macro-level intervention here, which is the deployment of the MSME energy map of India.
And the energy map is a profound strategic tool.
Yeah.
Yes. Applying Lens 2, which is control points, and Lens 5, which is power law relevance, reveals that this map functions as a highly potent latent control point for the entire MSME sector.
Okay, wait. How does the data architecture of a geographic map function as a control point for physical energy optimization? That seems a bit abstract.
It does, but think about it like this. Prior to the aggregation of this data, the layer that controlled outcomes was localized inertia.
Yeah.
If a government agency, or say a well-capitalized ESPC operator, wanted to deploy resources to optimize foundry efficiency, the friction of discovering the optimal deployment targets was higher than the friction of the actual mechanical fixes.
Oh. It was harder to find the broken machine than to fix the broken machine.
Exactly. You were flying completely blind. You had to rely on anecdotal relationships just to find clusters willing to adopt new practices.
Basically knocking on doors.
Right. But the MSME energy map fundamentally alters that dynamic by creating structural legibility.
The scale of the data they aggregated is just massive, too.
Yeah.
The documentation notes they initially profiled 43 clusters consuming 1.7 million tons of oil equivalent, or MITO.
Yeah.
But then they expanded that database to cover 83 clusters with a cumulative energy consumption approaching 10 MITO. And for you listening, to ground that number, 10 million tons of oil equivalent is roughly equivalent to the entire annual industrial energy consumption of a small developed nation.
It's a staggering thermal and electrical load on the Indian power grid. And knowing that roughly 20% of that load is bleeding out through degraded two-carry seals, slipping V-belts, and endlessly rewound motors, it makes the map an actionable targeting system.
Because the map's data architecture allows users to filter by highly specific, energy-intensive MSME sectors.
Yes, the interface allows for very granular filtering.
You can isolate food processing, glass and ceramics, light engineering, chemicals, textiles,
Yeah.
and specifically foundry and forging.
Right. You can cross-reference the sector by state and by exact geographic cluster.
So this searchability, it executes Lens 5 perfectly. Power law relevance demands that interventions are ranked by strategic impact. We cannot treat all industrial bottlenecks as equal. We just don't have the resources.
No, we have to isolate the small number of control points that yield disproportionate returns.
Right, so an ESPC operator armed with this map no longer guesses where to deploy capital. They don't have to knock on doors. They can analyze the entire subcontinent and pinpoint the exact geographic clusters exhibiting the highest density of inefficient energy consumption in the foundry sector.
They can identify the power law targets.
Yeah. If an investment fund allocates $1 million to deploy IE3 motors and edge compute ESPC contracts, the map dictates exactly which cluster in Howrah or Rajkot will generate the fastest, highest margin return on investment.
While simultaneously pulling the maximum megawatt strain off the local grid. It's highly efficient capital deployment.
So the map is a latent control point because it organizes all that fragmented, chaotic consumption data into a legible hierarchy of opportunity.
Exactly. Once the 10 mito of consumption is made visible and that 22% waste margin of BOP is quantified, targeted intervention becomes inevitable.
Right.
The map lowers the friction of discovery, allowing the simple payback logic of the ESPC model to actually scale nationally.
Okay, so we've moved from the thermodynamic realities of a leaky cupola furnace, right? We examined the misaligned incentives of motor rewind shops.
We broke down the zero capex mechanics of the ESPC contract.
Exactly. And we analyze how mapping 10 mito of fragmented data creates a national targeting system for optimization. That's the whole journey. But the restorative engineering text pushes this framework into a highly speculative bleeding-edge application.
Oh, this is my favorite part.
It's sci-fi level stuff.
Okay.
It details an industrial project recommendation that applies advanced edge compute artificial intelligence directly to these localized mechanical bottlenecks.
The synthesis of localized mechanical engineering and advanced edge inferencing, this is where the ESPC model truly evolves.
That text outlines an architecture based on a highly specialized, localized AI model. And it refers to it, and this is a wild name, as the Google Gemini Nano Banana 2 Pro architecture.
It's quite a mouthful. But the project itself is specifically titled Acoustic Edge Monitoring for Foundry Blower Degradation.
Acoustic edge monitoring. So we are moving way past just industrial clamp meters checking amperage. We are deploying localized AI to continuously listen to the acoustic signatures of mechanical failure.
Right. The recommendation explicitly advises operators to stop merely swapping motors. The evolution of the ESPC model requires deploying a localized, low-cost edge AI module prior to the mechanical intervention.
Okay, so how does this hardware work?
Well, the hardware relies on an acoustic sensor paired with a lightweight edge compute unit.
Now, when we say edge AI, for you listening, that means the inferencing and signal processing are happening directly on the silicon attached to the machine. Nothing is being pushed to a cloud server.
Which is vital because cloud latency and connectivity issues in a heavily shielded remote metal foundry.
It makes centralized AI completely useless.
Right. The compute has to live directly on the machine.
So the deployment mechanics are crucial here. Step 1 dictates using advanced CAD software, like Siemens NX, to design a rapid prototyped 3D printable magnetic housing for the acoustic sensor array.
And this housing must include necessary thermal shielding, obviously, to survive the ambient temperature of the blower casing.
Because it's sitting right next to a furnace.
Exactly. Then step 2 involves magnetically attaching the self-contained sensor node directly to the forced draft blower of the cupola furnace.
Okay, so you are slapping a 3D printed magnetically shielded edge compute node onto a vibrating high-temperature industrial blower in a room where the ambient noise level is already deafening.
Yeah, it's loud.
How does an acoustic sensor isolate the sound of a single failing bearing from the chaotic roar of a heavy foundry floor?
It seems impossible, right? But the edge compute utilizes fast Fourier transforms, or FFTs, to break down the complex ambient waveform into its constituent frequencies.
Okay, so it chops up the noise.
Basically, you train the lightweight AI model to aggressively filter out the low-frequency roar of the furnace itself,
Got it.
and instead it isolates two highly specific high-frequency sonic signatures. First, it identifies the exact vibrational frequency of a degraded, repeatedly rewound induction motor bearing.
Wow.
Second, it listens for the highly specific high-pitch hissing frequency generated by high-pressure combustion air leaking through degraded tuyere seals.
So the AI isn't just logging amperage drops like the old clamp meters. It is continuously monitoring the specific acoustic fingerprint of mechanical degradation.
Exactly. It knows exactly when the mechanical friction is compounding before it even registers as a critical electrical fault.
It's predictive.
Highly predictive. Step 3 requires the sensor node to log this isolated acoustic degradation data and correlate it locally with the power draw over a 48-hour cycle.
So you are gathering irrefutable, localized, multimodal data, sound and electricity.
Yes. But step 4 is what fundamentally alters the economics of the entire intervention.
Right, because the data isn't just proving the failure to the ESPC operator. The edge compute node feeds an automated LLM, a large language model workflow.
Right. The LLM workflow ingests all the raw edge data. The acoustic FFT analysis of the tuyere hiss, the frequency of the bearing degradation, and the correlated amperage draw.
It takes all that in.
And the system automatically processes that data and generates a mathematically precise, localized ESPC proposal for the foundry owner.
It writes the pitch.
Yes. It details their exact OPEX losses down to the dollar over that 48-hour window.
That is incredible. The diagnostic hardware acts as its own business development agent. The sensor array effectively writes the sales contract.
You are deploying a self-contained diagnostic and financial agent. The multimodal data proves the mechanical failure beyond any reasonable doubt.
Because it's literally showing them the sound of their money evaporating.
Right. The automated LLM report secures the financing agreement by demonstrating exactly how much capital the foundry is bleeding. Then the operator executes the physical fix and extracts the recurring revenue based on the delta.
So the technology automates the data collection, the failure analysis, and the contract generation. It creates this highly scalable, high-margin optimization pipeline built entirely on verifiable physical data.
It perfectly executes the core philosophy we talked about. He who owns the baseline data dictates the terms.
It really does. But beyond the highly optimized business model, the text grounds this entire operational framework in a deeply human philosophy.
Yeah, the author's personal anecdote at the end is really powerful.
It is. The author shares this story, noting that years ago they watched factory workers handle live explosives with absolute mechanical caution. And that prompted the engineering of a TechMan cobot process to physically remove the humans from the kinetic danger zone.
Right. And the author connects the engineering of those explosive handling cobots directly to the optimization of these MSME foundries.
How so?
Well, whether you are building automated systems to protect explosives handlers, or engineering advanced bioprinters for human tissue, or deploying edge AI to optimize a leaky pneumatic pipe on a dirty foundry floor, the fundamental mechanics of system optimization remain identical.
The underlying goal of the engineering is exactly the same.
Exactly. The author distills this into a permanent lesson. They wrote, "Real technology doesn't replace people, it restores them."
It restores them. I love that.
Think about the run-to-failure culture in these foundries. The massive ambient heat, the deafening noise of the pneumatic leaks, the continuous financial stress of the degraded motors. That entire ecosystem is deeply degrading to human capability and safety.
It's just a miserable place to work.
It is. By optimizing the physical system, by applying edge AI and ESPC financial structures to fix a simple mechanical leak, you are doing far more than just reducing electrical draw.
You are making the facility safer, quieter, and financially viable.
Exactly. You're restoring the operational dignity of the people working on that floor. As the author states, hope and efficiency must be made tangible.
Hope and efficiency must be made tangible. That is a perfect summation. We have mapped an incredible operational architecture today. We started by identifying the thermodynamic reality that massive electrical bills are often the downstream illusion of a physical failure.
Yeah.
Specifically, 20% pneumatic leaks of the tuyeres and severe turbulent friction in the delivery piping.
And then we analyze the deeply misaligned incentives through Lens 4, identifying the local motor rewind shops as beneficiaries of obscurity, profiting from the continuous degradation of magnetic core efficiency and that run-to-failure culture.
Right. We broke down the mechanics of the energy savings performance contract, demonstrating how an operator bypasses the CapEx bottleneck by financing the IE3 motors and piping upgrades themselves.
Capturing the revenue delta by strictly controlling the irrefutable baseline data.
Exactly. Then we zoomed out to the macroeconomic data from Samiccia, discovering that 22% of potential energy savings relies entirely on best operating practices, and that fragmented knowledge remains the ultimate structural barrier across the subcontinent.
Which led us to explore how aggregating 10 million tons of oil equivalent into a searchable MSME energy map creates a latent control point, allowing ESPC operators to target power law interventions.
And finally, we looked at the deployment of 3D-printed acoustic edge AI, utilizing fast Fourier transforms to isolate the hiss of a leak, and employing automated LLMs to generate the financial contracts that ultimately restore the human element of the factory floor.
It is a comprehensive framework. It really demonstrates that true industrial optimization requires mastering the mechanical physics, the financial incentives, and the data architecture all simultaneously.
It really is a masterclass in restorative engineering. So I want to leave you, our listener, with a final thought to analyze in your own operational environment. The text proves that the mechanics of system optimization are discipline agnostic.
Absolutely.
So look around your own industry, your own supply chain, or even your own daily operational processes. What is the induction motor you keep endlessly rewinding because it's culturally easier than auditing the root cause?
What's your blind spot?
Right? Where's the pneumatic leak you were ignoring? And critically, who is the beneficiary of obscurity profiting from that specific decay? Because the golden rule of the ESPC model applies everywhere. He who owns the baseline data dictates the terms. So you must ask yourself, who owns the baseline data of your life?